Here we are again. We're going to continue with titration, and today it's going to be titration of a weak acid with a strong base. So this is different than the titration that we did before with a strong acid and strong base. These are longer problems, a little bit tougher, but kind of putting together the whole thing with buffers and with titration of a strong acid, strong base. So here we go. So with the titration of a weak acid and a strong base, the reaction is essentially going to go to completion. But the problem is that when you react your acid, your weak acid, which we'll just get a pen here. We'll just call it HA because it could be any weak acid. So when you react your weak acid with a strong base, so all we care about from the strong base is the OH minus, you get not just water, but you get the conjugate base. So it's this conjugate base that is affecting the pH. So when you've added exactly as much OH minus as weak acid, you won't just have neutral salt water. You'll have some conjugate base in there that will affect the pH. So the beginning part is the same as doing the strong acid, strong base. With your stoichiometry, you always have to react how many moles of each have reacted, and then what you have left is then what will decide your pH. So when you have some weak acid and its conjugate base, you could use the shortcut of the Henderson-Hasselbalch equation. When you only have weak acid or you only have weak base, then it's an ice problem. Okay, so we're going to have a combination of things. We're going to have an ice problem. We're going to have a buffer formed, so we can use the Henderson-Hasselbalch equation as our shortcut, and we still have to do the stoichiometry part. Okay, so it's multi-step. If we plot the titration curve for it, the pH at the equivalence point is not 7 for a weak acid, because again, there's still conjugate base at the equivalence point. It's not just salt water. Okay, so the titration curve looks different. The beginning part is longer because it's buffered. We're creating a buffer. And then there's a shorter rise. And then the equivalence point is going to be more like pH 8 or even 9, could be, depending. It's not going to go down like that. It's going to go like that. Okay, so we'll get back to that later. So if this is our problem, calculate the pH during the titration of 40 milliliters of 0.1 molar propanoic acid, which we're just going to abbreviate HPR. The Ka is 1.3 times 10 to the minus fifth after each of the following volumes of 0.1 molar NaOH has been added. So initially, we have no NaOH added. So all we have is some 0.1 molar propanoic acid. So this is just a regular ice problem. All we have is this weak acid that we need to find its pH up. So we set up our ice problem. We have our, let's move this up here. We have our propanoic acid in water, and it's going to make its conjugate base and H3O plus. So it's 0.1 molar, 0, 0, and so then it's minus X, plus X, plus X, X and X, 0.1 minus X, a typical ice problem with a weak acid. When we solve for X, then that will be our, in this case, all these things are in the way. That will be our H3O plus concentration right here. We solve for X. So X squared, X times X over 0.1 minus X, just like our regular weak acid ice problems. The Ka is to the negative fifth, so we can ignore this minus X from the 0.1. So we'll just have x squared over 0.1 equals the Ka. So x squared equals 1.3 times 10 to the minus 6. When we multiply that 0.1 over, we solve for x, and it's 0.0011 molar. That is our H3O plus. Okay, so regular ice problem, because all we had in there was the weak acid. So minus the log of 0.0011 gives us our pH, and that comes out to be 2.96. So that's another difference in the titration curve of a weak acid. We're going to start at a higher pH than if it was a strong acid. So the pH is almost 3 for this weak acid by itself. Okay, then next we're going to add 30 milliliters of this base to it. Okay, so the next step, just like with our strong acid, strong base titration that we did before, you have to calculate moles of each thing that are added together. So originally we have 0.04 liters of 0.1 molar of the weak acid. So multiplied together, we have 0.004 moles of our weak acid. Same thing with our NaOH. We're adding 30 milliliters, which is 0.03 liters, times 0.1 to get our moles of OH minus. Those completely react together. So what is going to happen in our reaction, if we want to write it out, we can do this as what's called a BCA problem. BCA is before, change, and after. And this is in moles. This is the stoichiometry part. So it's different from ice because it's in moles. Whereas in the ice problems, that's in molarity. So with the BCA, this is for stoichiometry reacting our acid with our base. It's a single arrow because it's not reversible, okay? So we start with our weak acid, and we're adding to it the NaOH, which is a strong base, so it's the OH minus is all we care about. It's the same concentration. And they're going to completely react together. Originally, we have no conjugate base yet. But when they react, this is our change. It's going to be that they completely react as much, the lowest number of whichever one gets used up is our amount. So we have 0.003 moles of this and 0.004 moles of this. So 0.003 moles of each can react. That's going to form 0.003 moles of our conjugate base. And then water doesn't have a concentration just like in the ice. So then that leaves us 0.001 moles of our weak acid left over. All the OH gets used up, that's 0. And we have now formed 0.003 moles of conjugate base. Putting those back into concentration is important. Okay, so you have to convert them back to molarity, dividing by the total volume. So we had 40 milliliters of the one and 30 milliliters of the other. So that's a total of 70 milliliters total. So we divide our moles by the 70 milliliters in liters, 0.07, and that gives us the molarity of our weak acid and its conjugate base. Okay, so those we could then do another ice problem with, or since we have some weak acid and its conjugate base, we can just use the shortcut of the Henderson-Hasselbalch, just like a buffer, because that's what we've created. We've created a buffer. So plugging in to the Henderson-Hasselbalch, which is pH equals pKa plus the log of the base over the acid, we can get the pH. Okay, again, we could have done this with a ice problem too, be the same. I'm not sure why this isn't going away. Go away. It's changing color. There we go. Okay, so the Henderson-Hasselbalch, pH equals pKa plus the log of the base over the acid. So minus the log of the Ka is the pKa, and then the conjugate base goes on top, concentration, and the conjugate acid concentration goes on the bottom. Okay, base over acid. So when we solve that, we get a pH of 5.4. So the pH was close to 3, and now adding 30 milliliters, we added quite a bit of the NaOH, it jumped up to 5.4. But we still have some of the conjugate acid left over. We haven't neutralized all of it. So we'll keep going. Next, we're adding 40 milliliters of the 0.1 molar NaOH. Now in this case, we've added, we still have 0.004 moles of our weak acid, 40 milliliters of 0.1 molar. Now we're adding 40 milliliters of 0.1 molar OH minus to it. So we have 0.004 moles of both. Those are going to react completely so that we have used up all of the weak acid, and what we are forming is its conjugate base. Okay, so this is the equivalence point. Okay, we've added enough OH minus to react all of the weak acid. And what we formed is its conjugate base. So here we have 0.004 moles of conjugate base. We need to put that back into molarity by dividing by the total liters. So we had 40 milliliters of acid, and we added 40 milliliters of NaOH. So we get a total volume of 80 milliliters or 0.08 liters. So dividing the moles by the liters, we get the molarity of our weak base. We have to use that to find the pH still. So we did all the stoichiometry part, figured out how much weak base we have. We still haven't found pH. So now we have to do a weak base ice problem. And for that, we need the Kb. Well, Ka times Kb equals 1 times 10 to the minus 14th. So to find the Kb, we divide 1 times 10 to the minus 14th by the Ka, and that will give us the Kb. Okay, that's how we get Kb. And then we're going to do a nice problem again. So this time we have pure weak base. That's all that's left over. Pure weak base. All the weak acid got reacted. So then the weak base in water will produce conjugate acid and pure OH minus. So with our weak base, it's 0.05 molar. This has to be in molarity. You can't just plug moles in there. So 0.05 molar, 0, 0. Water doesn't have a concentration. We're going to lose X amount of the weak base as it forms X amount of its conjugate acid and X amount of OH minus. So then we'll have 0.05 minus X, X, and X for our amounts. So now for our Kb, we'll have X times X over 0.05 minus X equals the Kb, which when we divided 1 times 10 to the minus 14th by the Ka, we got the Kb. So 7.7 times 10 to the minus 10th equals X squared, and this is where it's a really tiny number, so X is going to be really small, so we can just call that 0.05. We can ignore that minus X. Okay, and we solve for X here, and X comes out to be 6 times 10 to the negative 6. That is our OH minus concentration. So then to find our pH, we can take minus the log of our OH minus concentration. So log of 6 times 10 to the negative 6. So our POH comes out to be 5.22. And we subtract that from 14. And I get 8.78 actually. Just keeping, I wasn't very good about keeping sig figs on this. You guys should do a better job of that. But our pH comes out to be 8.78, okay? And so that's the equivalence point, right? And that means all of the weak acid has been used up and it formed its conjugate base. Now, if we keep adding NaOH to it, then we're gonna have excess NaOH. So the next one said, well, what happens when we add 50 milliliters of NaOH to our 40 milliliters of 0.1 molar acid? We still have 0.004 moles of our weak acid. We've now added 50 milliliters, so that's 0.005 moles of our OH minus. Same, they react completely. So in the stoichiometry, that has to be in moles. BCA, before we have 0.004, 0.005, they react completely, but you can only use as much acid as you have. So they're both gonna lose 0.004 moles, but then it's going to form 0.004 moles of its conjugate base. So we subtract that out, that's 0, that ends up with 0.001 moles of pure OH left and 0.004 moles of weak base. At this point, we have 0.001 moles of pure OH minus. That weak base will form a little more OH minus, but it's not going to be that much because it's a pretty weak base. So we can pretty much ignore this and we can just focus on this amount. Because again, if we added 0.0001 moles of OH to this, it really doesn't change the value. So again, it's going to be a small amount of OH from this formed. So we're going to ignore it. And we're just going to say that's how much we have, 0.001 moles of pure OH minus. We do need to put that back into a molarity. So now we've added 40 milliliters of acid to 50 milliliters of NaOH for a total of 90 milliliters. So the moles of OH minus divided by the total volume of 0.090 liters gives me my molarity of my OH minus, which is 0.011. So now I will find the POH, which is minus the log of 0.011, and that is, calculator, log of 0.011. That is 1.96. So that means the pH is 14 minus that. So the pH is 12.04. That's a 12. Okay, and that is the end of our titration then. So our titration curve would look pretty different from the strong acid one. It would have started higher at almost 3. It would have risen more slowly because as you're adding base to the weak acid, you're making this conjugate base. When you have some of each, that's a buffer. So it rises a little slower, and then it has a shorter jump, and then it will go up again. And the equivalence point in this case, it was what was it, pH of 8.78. So, oops, sorry about that. Okay, so 8.7 or 8.8 is the equivalence point in this one. And then it would go up a little bit more up, and then it would be pretty steady. It was actually a little higher, pH 12 than was what it went up to, okay?